Okay, so here's an example of a problem where we can now utilize our new equation, E equals h nu, that describes the energy of a photon, to actually calculate how many photons are contained in a laser pulse. Okay, so we have a nitrogen laser that emits with a wavelength of 337 nanometers. Okay, the total energy of this pulse is 3.8 millijoules. So you can think of that. Of course, laser pulses have, you can think of laser pulses emitting lots and lots of photons at one point in time. That's why they're very, very bright light sources. But of course, the total energy of the laser pulse is the summation of the individual energies of the photons, which of course is dependent on the frequencies. Okay, so what we can do here is we can actually calculate the frequency from our wavelength by, of course, using our C equals lambda nu equation. We can utilize the 3.0 times 10 to the 8th meters per second. Of course, our speed of light is in meters. The wavelengths that we're given is in nanometers, so we're going to have to convert that. We can do it all in one step down here. Of course, there are 10 to the 9th nanometers in 1 meter. And if we convert this to meters and divide that by, or divide 3.0 times 10 to the 8th meters per second, our meters are going to cancel out and we're going to be left with reciprocal seconds, which is of course what we want. And that gives us a value of 8.90 times 10 to the 14th reciprocal seconds. Okay. Now what we can do is we can plug that frequency into our equals h nu calculation, and we just saw that Planck's constant h is 6.626 times 10 to the negative 34th joules seconds. And multiplying that by 8.9 times 10 to the 14th reciprocal seconds, our seconds are going to cancel out, and what we're going to be given is units of joules for energy, and of course this will be 5.59 times 10 to the negative 19th joules. Okay, and that is the energy of one photon of light with a wavelength of 337 nanometers. From the problem, we were given that the total energy was 3.83 millijoules. Okay, and so what we can do is we can, of course, convert that into joules, dividing it by 1,000 millijoules in 1 joule, and then using that to determine our number of photons. So we can think about this as this is the joules per photon. Okay. Now if we take our 3.83 millijoules, that would be 3.83 times 10 to the negative 3rd joules, and we use this as a conversion factor, we can see that 5.59 times 10 to the negative 19th joules per 1 photon. Joules are going to cancel out, and what that is going to give us is a value of 6.85 times 10 to the 15th photons. So in one pulse of this nitrogen laser, we have 6.8 times 10 to the 15th photons. Okay, so the next topic we're going to discuss about light, which will lead us directly into its connection with the electron, and that is, of course, emission. We briefly talked about the absorption of light and how the light that isn't reflected, we view its colors for objects in everyday life. And again, remember that white light spectrum is, of course, white light consists of all the wavelengths of visible light, and it's generally a continuous spectrum. Okay, we think about the white light spectrum as continuous. Okay, meaning that there's no breaks in this region of the electromagnetic spectrum. Now it turns out when you look at different sources of light other than sort of maybe the light bulbs in this room or the sun, you often get spectrums of light that are not continuous or have many breaks where there's not wavelengths of light, or what we get is discrete emission of specific wavelengths. And that can be viewed here with a hydrogen lamp. Okay, everyone's seen neon lamps. And this would be, of course, a hydrogen lamp where the hydrogen gas is put into a glass tube just like neon is. Of course, we're going to give that energy. We're going to apply a potential across that glass tube, and that energy is going to cause the hydrogen to emit light. Okay, if we just look at the color of the emission of hydrogen light, it's sort of this purplish color. If we send this color of wavelength, or this color of light, through a prism to separate the component wavelengths, just like we did for white light, what we see instead of a continuous spectrum is a very, very discrete emission spectra with just a few specific wavelengths. And it turns out no matter how much energy you put into hydrogen or what hydrogen lamp you use, you are always going to see these very specific wavelengths of light. And it turns out you can do this type of experiment with other elements. Here's helium and barium. And again, if you excite these elements, they give you very specific emission spectra that correspond to that and only that atom. Okay. Now it turns out that this was one of the biggest keys to unlocking some of the mysteries of how the electron was dispersed or sort of held within the atom. And one of the first scientists to propose a mechanism for this distinct spectra for each element was Niels Bohr. Okay, and he gave the Bohr model of the atom. Okay, and what he proposed is that electrons orbit the nucleus in very specific intervals. Okay, he called them orbits, and his proposition was sort of analogous to sort of planetary models: planets orbiting the sun, electrons orbiting nucleus. As we'll see, it gets a lot more complex than that simplistic model, but this is a good starting point for discussing them. Okay, so he said that electrons exist in specific orbitals, which will give them, which we will now eventually call them energy levels, but right now we'll give them n numbers. N equals 1, 2, 3, or 4, the different orbitals. Okay, now we know that the electron is attracted to the nucleus, positive charge, protons. And it turns out that as the closer the electron gets to the nucleus, the more stabilized it is, the lower energy. The further away the electron is, the higher the energy. Okay, now it turns out that if you excite these atoms, like we did in the hydrogen lamp, remember we had hydrogen in a lamp and we gave it energy, we excited it, gave it energy. What we're doing is we're exciting the electrons from low energy levels, say n equals 2, we excite them to higher energy levels, say n equals 5. Now, of course, when that electron is in a higher energy level, it is less stable, so eventually it falls back down to a lower, more stable energy level. When that happens, when an electron transits from a high energy level to a lower energy level, it emits a photon, and usually we use the h nu for a symbol for a photon. It emits a photon whose wavelength matches exactly the difference in energy from those two energy levels or two orbitals. Okay? Since going from n equals 5 to n equals 2 is a bigger energy transition, more energy than, say, going from n equals 4 to n equals 2, the photon that is emitted is a longer wavelength, lower energy photon. And the same can be true for, say, an n equals 3 to n equals 2 transition. That energy difference is going to emit a photon. That photon has a longer wavelength than both of the previous transition we discussed about, because, of course, energy is proportional to frequency, inversely proportional to wavelength.